to another AQA AS Chemistry video. So today I'm going to be just doing questions based off of what we just done with percentage yields and atom economy. And basically I'm going to go through a practical. That's the main one that comes with percentage yield and atom economy, and that's with called crystallization. And I don't remember the number on the practical booklet, but I'm pretty sure it's one that you should know. And you should know it from GCSE at least. If it doesn't come up in A-level, but I'm pretty sure it comes up at least in GCSE, but here we're talking about A-level, of course, but I'm pretty certain that you need to know it for A-levels as well, crystallization. But either way, it's the one example that you should be familiar with, and it's related to percentage yield and atom economy. Alright, so got a question here. So, a student has a solution of blue hydrated copper sulfate, CuSO4x H2O, which means the X is the number of H2O, but we don't know it yet. They've just said X, so it could be as many H2Os as they do please. The student wants to obtain pure hydrated copper sulfate. I'm going to just talk through it, right? I'm going to talk through the practical because I'm not going to do this. Is originally the question, but I haven't actually gone through it, so I don't think it was fair to make it a question, right? So, what technique should the student use? Sorry, I have retainers on, so my voice is a bit muffled. But the student could use crystallization to obtain hydrated copper sulfate. So crystallization is the separation technique used to separate soluble solids from a solvent. Right. So remember what solutions are. Solutions are a solute that's been a salt of some sort that's been dissolved in a solvent, which is water usually, right? So and then now we're just doing the opposite part, where instead of dissolving it, we're separating it out and crystallizing, forming those crystals again. So the student would need a tripod, so I'm just going to name the third. This is the third point. We'll be talking about the equipment that we'd use. Sometimes in the exam they ask you just to draw the apparatus, and if it was to draw the apparatus, it would just be a as I said before, tripod and gauze. It's a makeshift Bunsen. It's a makeshift it's makeshift water bath with an evaporating basin on the top, right? That's essentially what it is. I'll also do it here, right here. I can. No, I can't. Doesn't matter anyway. But you get what I'm trying to say. So a student would need a tripod of a gauze. On top of the student would need a evaporating basin. The basin would need to be heated by a Bunsen burner. So you basically have an evaporating basin on top with your essentially the liquid that contains your. It will be your solution essentially. Your crystals would form here, right? I don't know why it's done that, but I'm just gonna leave that as that. And it'll be on top of a beaker, and then that's on a tripod and gauze. And then you have you'd have your Bunsen burner here. I could use a yellow flame, but that's a terrible flame. I can't draw a flame. Ideally, you get the point. I tried to do it, and you label it. You say your Bunsen burner, your tripod, your gauze, your beaker with water in it. Essentially, that's acting as a water bath. So, beaker with say 100 centimeter or 500 centimeter cube beaker, and then your evaporating dish on top, which has your solution. Right. That's what they said to draw it out. But describing the process now that we'd filter. So when we actually forget about this part here, when we actually we'd add our for example, if we wanted to get hydrous copper sulfate, right? Because this is what we're trying to form. We're trying to form pure hydrated copper sulfate. So we would get pure copper sulfate or anhydrous copper sulfate, and we'd mix a certain number of it, or certain mass of it. We'd weigh out certain mass. We'd first of all, we would write out our equation. We'd write out how much of it we need, and we would add. Usually, we just add just over an excess of what we actually need until it starts to. We add just over an excess, so we have just enough of it, and then any excess that we have, so any that doesn't dissolve in our solution, we would filter out. So we'd filter out the solution to remove any insoluble solids in excess, so any of the insoluble copper sulfate that hasn't dissolved, right? And heat the solution. We then heat the solution to boil approximately half of the solution, and we would leave the remaining solution to cool and evaporate over time, usually overnight. But you can just do it. I mean, if you're doing it practical, you don't really need overnight, to be honest. You can just do it, leave it for like half an hour or something like that. It will usually cool down. But ideally, cooling it down, like giving it enough time to cool down. And when the crystal, this is your crystallization point here, right? The more time you give it, the more, if the more time you give it, the more crystals form, or more likely it is that you get your crystals forming. Remember, one of the things we were talking about in percentage yield was having enough time for the reaction to happen. So the more time we give it, the more time it has to cool down and for the crystals to form. And when the crystals are formed, we would pat them with tissue or paper. I can't speak. When the crystals are formed, we pat them with a tissue or paper towel to dry them, and this is called blotting. We blot them dry. The reason we do this, and this is quite an important thing that they always ask in the exams, this fourth point here, why we do that, is to remove excess water, which would act as it's an impurity. Excess water that's on top of our crystals, on the exterior of the crystals, that's added weight, and that's what causes us to have a percentage that's more than 100%. It's an impurity, because we don't actually need it. It's not part of our product. It makes our product look much larger than it actually is, and so we just plot them by lightly pressing them down. You'd get. I was gonna get a tissue. I actually know what I have them. If we had crystals in here, we put it down and we lightly press it down, and then we let the water absorb in the tissue, and then we would scrape off our product back into the evaporating basin. But that's essentially how it would go down, right? So that's the practical there, and now I'm gonna go through a question, right? So the student forms 2.56 grams of the hydrated salt. They then reheat the crystals until constant mass. The mass of the crystals decreases by 31.25%. Uses information to calculate the value of X in CuSO4.XH2O. The mass of, and then the MR, I should say, this should be mass, MR is yes, I could pause that, shall I? You get what the point is. The MRs are here represented. That should be 64 point. Is that 64? Copper 63.5. I don't know why it says 64. Sorry, I copied this from somewhere. I copied this from Seneca, actually, so it might not be 100% correct all the time, but yeah. MR 63.5. In A level, you can't just get away with 64. You can't get away with 32.1. It has to be 6. The only one you can get is unless it's a full number like 16.0. But yeah. Anyway, let's get to the actual point of the question. So the student forms 2.56 grams of hydrated salt. They then reheat the crystals until constant mass. The mass of the crystals decreases by 31.25%. Uses information to calculate the value of X in CuSO4.XH2O. Forget this R, S, and T part. That's just me trying to, and it does that automatically. It's just a question there. But all right. So what's actually going on here? So we have our hydrated salt, and then they've reheated it. All right, and the mass of the crystals will decrease by 31.25%. So when you have this, right, you have this, and you've heated it, which means that you would evaporate the water that's left. So this 31.25% that's decreased means that you're going from CuSO4. Let me actually do the equation that you're actually doing. You're going from CuSO4.XH2O solid, because it's now out the basin now, and you're heating it, and then you're forming CuSO4 solid plus XH2O. That's the only two things. It's a thermal decomposition reaction. That's what it is, right? If the mass is decreased by 31.25% to get to here, which means that this is 31.25% less than this, which means that 31.25% decrease must be the mass of a H2O. Because if this has gone down, by 31.25% to get to the crystals, which is CuSO4, which means that this is actually probably gas if it's evaporated. So I believe that it means that the 31.25% must be the H2O. Therefore, if I wanted to just get the mass of H2O, it'd be 2.5. So, sorry. Mass of H2O is equal to 2.56. 2.56 times by 0.3125, which would be equal to 0.8 grams. And then that means the mass of CuSO4 is just the rest of that, which is just 68.75%. Yes. Yeah, 68.5%. So I could just do 2.56 minus 0.8, but it's the same thing really. It should be the same thing. So 2.56 multiplied by, in real life, just do one of them. You don't have to do both of them. I'm just showing you that it's the same either way for both of them. So 0.6875, and that would equal 2.56. It's the same as 2.56 minus 0.8. Whatever's left over from, right? 2.56 minus 0.8, that's just going to be 1.76, right? Let me just double check this just to make sure that this is correct, but it should be. I don't see why it shouldn't be. Unless I've done the wrong one, times by 0.6875. Yes, it's the same thing. Right, so we have the masses of either. We need to find out the moles. Moles of H2O would be equal to 0.8 over 18. The moles of CuSO4 is equal to 1.76 all over 63.5. Usually just add it separately, show you can add them up separately, but just to show you where it is, 32.1 plus 64, or 16 times by 4. Zero 0.8 over 18 is 0.04. 0.044. I'm gonna have it as that, and then for SO4, did they say they want in number of significant figures? They didn't. No. 3 significant figures is the least in the exam, so I usually actually go for 444. That's the least number. Or 1.76, right? 1.76 over 63.5 plus 32.1 plus 64. 0.0110. Right, so now comparing, that's the moles of this, right? So for every 0.0110 moles to there's 0.0444 moles of H2O, right? And that's the mole ratio between that to, so if 0.0110 to 0.0444, and that's roughly a 1-to-4 mole ratio. Therefore, X must be equal to 4. I'm going slow in these videos. Usually you do that much quicker, but I'm just doing it for the sake of trying to explain to you. So if you want to just skip ahead, I'm going to do the next question. So if you just want to skip ahead to find the answer, just do that. But I'm just trying to explain. All right, question 2, right? A student heats calcium nitrate crystals causing the following reaction. 2 calcium, also 2 CaNO3 plus 2 calcium oxide goes to plus 4NO2 plus O2 gas. The student collects the gas that is released. Calculate the volume of gas that would be collected if the student heated 1.312 grams of calcium or CaNO3 plus at 25 degrees Celsius and 100 kilopascals. Give your answer in decimeters cubed to three significant figures, and then that should be MR again. I don't know why he keeps doing that, but I don't know. I just copied that. I say why I didn't do it. I copied it. The MR of calcium is 40.1, nitrogen 40.0, 16, and oxygen is 16.0, and obviously your gas constant 8.31 joules per carbon per mole. I pause the video now and try and answer the question. Alright, I'm gonna assume that you pause the video now and you answer the question, right? So, alright, so first we need to understand what's actually going on here. So they've given you the equation, so I have to write that down. But they want you to calculate the volume of gas that would be collected if the student heated 1.312 grams of the reactant. And now the reaction conditions, they're all happening in the same vessel, so that means that the conditions that are happening on the reactant side are the same as the conditions in the product side, so we don't have to worry about that, right? The gases, we're only concerned about these two here. Those, we're not concerned about calcium oxide because that's the solid, it's not gas. They said the volume of gas that would be collected. I don't know why it doesn't do that, but I'm trying to get this to highlight. That work? Yes. Alright, calm. Calculate volume of gas that will be collected. I'm just wasting time right now, to be honest. I should just be answering the question. But anyway, the first thing I would do with this question, I would just go for moles of calcium. I want to know the moles of that. In all these questions, right? In chemistry, from what I've understood, you always get a mole for these questions, just writing out the moles. So if you ever get a question in your exam and you just completely have no idea what's going on, and you're freezing and you're thinking to yourself, oh, maybe I'm wasting time now, the one thing you should always do is just work out the moles. You always get this, always a mark for working out the moles. And even if they're not related, just put down the moles of this question. Sorry, moles of this compound, moles of this compound, moles. You're always gonna get a mark for that. So, but in this case, we need to just work out the moles first. So moles of calcium or CaNO3 or calcium nitrate, I should say, will be moles, the mass of the M or mass. If you need to just skip through this question, you already know how to do it, just skip to the answer. But if you didn't know how to answer the question, I'm going to go through it right now. So it's the mass over the MR, 40.1 plus 2 by 14 plus 48, or 16 times by 3. That's twice. 1.312 over 40.1 plus 2 by 14 plus 48. 7.99, why do I keep doing that? 7.995, I just go straight to round that to 8.00 times 10 to the power of minus 3. Alright, so there's, for every 2 moles of reactant, there's 4 moles of NO2 and 1 mole of O2. So it's a 2 to 4 to 1 mole ratio, right? The moles of NO2 is equal to, go from 2 to 4, that's just times by 2. 8.00 times 10 to the power of minus 3 multiplied by 2 is equal to 1.60 times 10 to the power of minus 2 moles. Should write that down. The units are important. Moles of I'll just get O2. Sorry, I'm just taking the piss now. 8.00 times 10 to the power of minus 3 divided by 2. To go from 2 to 1, divide by 2. And that should be 4.00 times 10 to the power of minus 3. Add these together. So the sum of moles of gas, sum of gaseous moles, product. Don't write this in the exam, I'm just trying to explain to you, you don't have to write all of that down. And that's equal to 1.60 times 10 to the power minus 2 plus 4.00 times 10 to the power minus 3 . So 4.00, I'll just say 4 times 10 to the power minus 3 plus 1.6 times 10 to the power minus 2 is roughly 0.02, or 2 times, roughly 2 times 10 to the power minus 2, right, moles. We have the moles now, so the equation is PV equals nRT when we're relating to this question. We want to get the volume, so volume is equal to nRT over P. Volume would be equal to 2 times 10 to the power minus 2 times by 8.31. I always put it in brackets when we do it because in the calculator, because you don't have any mistakes. The temperature is always is 298. You come to realize that 25 degrees Celsius, or room temperature, is always, it's easy to remember, it's 298. But if you don't know why it's 298, it's because it's measured in Kelvin. The units is Kelvin, not degrees Celsius. 25 degrees Celsius plus 273, because that's the conversion to Kelvin, and that's equal to 298 Kelvin. Right. Volume is equal to, say, over the pressure, which is 100,000 pascals, not 100 kilopascals, or 100 kilopascals is 100,000 pascals. Therefore, the volume is equal to, whatever that is, answer multiplied by 8.31 multiplied by 298 over 100,000 is roughly 4.95 times 10 to the power minus 4 meters cubed. But the answer, they were still not done yet because they said they wanted it in decimeters cubed, right? So in case you don't know what the conversion from meters cubed to decimeter cubed is, remember that in 1 meter cubed, it's in the name. Deci means 10 in Latin, or maybe it's Greek, I don't know, but deci means 10. So 1 meter is equal to 10 decimeters, right? If you're cubing that, 1 meter cubed is equal to 10 cubed decimeters cubed. So 1 meter cubed, one cubed is just 1, 10 cubed is 1,000 decimeters cubed. So 1 meter cubed is equal to 1,000 decimeters cubed. So if you want to get the volume, convert from meters cubed to decimeters cubed, the volume is equal to 4.95 times 10 to the power minus 4 multiplied by 10 to the power 3, or 1,000, to get from 1 to 1,000, times by 1,000, or 10 to the power 3. The volume is equal to 0.495, or 4.95 times 10 to the power minus 1 decimeters cubed. And those are the 2 examples there. Holding for time. Should I go do another question? I will do another. I plan to do more, so I'll. If you feel like this is just more than enough, I'm gonna just do actual past paper questions now. So where did I leave them? I left them somewhere. Organization skills. How the hell have I lost it already? Oh no, it's here. There we go. Yes. Alright, so that's done now, so I can just move this over here. The student investigation, so how should I do this on time conditions, or 14? And then why is this in single page? Oh, God, it's not single page. Yes, no, that's fine. Alright, well, 20 minutes. Should I do a 20-minute timer? 20-minute timer. Alright, so a student investigated the reaction of copper carbonate and copper oxide with dilute hydrochloric acid. In both reactions, one of the products is copper chloride. Describe how a sample of copper chloride crystals can be made from copper carbonate and dilute hydrochloric acid. So this question, I'd add a weighed mass of copper carbonate. Mass of copper carbonate was CuCO3, C2 plus, CO3 2 minus, yes, to a measured volume of HCl, of dilute HCl. Do it in bullet points. You see, it's not the same question, but the same principle relatively applies. I'd filter to remove excess. Filter to remove excess copper carbonate in solution. I'd say I'd heat the filtrate to allow for crystallization. So heat the filtrate. You heat in the filtrate to initiate crystallization. And then you'd leave, allow time for crystallization. Say I leave. So allow to cool. Allow crystals to cool. And crystallize. Great. So student wanted to make 11 grams of copper chloride. The equation of the reaction is so and so. Copper CuCl3 plus 2HCl goes to make CuCl2 plus H2O plus CO2. So and so there. Calculate the mass of copper carbonate the student should have reacted with dilute hydrochloric acid to make 11 grams of copper chloride. So to make 11 grams of copper chloride, so calculate the mass of copper carbonate. All right, so moles of CuCl2, 11 over, what was it now? 63.5 plus 2 by 35.5. I don't know what I'm destined to be. Okay, come. 11 over 63.5 plus 2 by 35.5. 0.08 or 0.08. No, 0.08. Yeah. And then moles of, it's a 1-to-1 molar ratio, right? 1-to-1 molar ratio, so moles of copper carbonate. If moles is equal to the mass over the MR, the moles would be the same, right? So the is equal to 0.08 mass of copper carbonate, mass equal to moles times by the MR, 0.08 multiplied by the MR, which is 63.5 plus 12 plus This is actually bugging me out. I feel like I should write this as 0.0818. Anyway, 63.5 plus 12 plus 48. And then that would be all equal to multiplied by 63.5 plus 12 plus 48. I'd write it, I wouldn't even leave it like that because I'd always write it as 8.18. Sorry, that's just bugging me out a lot. Times 10 to the power of minus 2 moles. They usually give you a bit more space to write anyway, but yeah. And you're left with 10.1 grams. 10.1 grams, so 10.1 grams. Alright, percentage yield of copper chloride was 79.1%. Calculate the mass of copper chloride the student actually produced. So it was they expected to get 11 grams, so 11 just 11 multiplied by 0.7 11 multiplied by 0.791. It should be 8.7 grams. 8.70 grams because it's freezing living in figures. Alright, so look at the equation for the two reactions. So two reactions are there. Relative formulas are there. The percentage atom economy for the reaction is calculated using. I'm reading this as if I was doing the exam. Like realistically, I just go to what the point of the question is before I really go in extensive detail into reading what the equation is and all that. Like really, the point is like looking at. They said look at the equation. You've done that. Relative, you already know the MRs of that. The percentage atom economy of the reaction is. We know the equation for atom economy is the MR of your desired product over the MR of all of your reactants. Calculate the percentage atom economy of the reaction 2. This is the main point of the question. Just calculate the atom economy, right? So of reaction 2, specifically at reaction 2. The desired product is CuCl2, so it will be 63.5 plus 2 by 35.5 all over 63.5 plus 16 plus 2 is 2H, so you have to multiply that to 2 by 36.5 times by 100, and that would be 2 by 35.5 over 63.5 plus 16 plus 2 by 36.5. Yes. Of course, it times by 100. Times that by 100, not bad. 88.19%, or 88.2% really. Three significant figures, right? Yeah, 88.2%. How are we doing for time? We're looking good. We're actually ahead of time actually. The atom economy of for reaction 1 is 68.45. Compare the atom economies of the two reactions for making copper chloride. Give a reason for this difference. It's a 1 mark question. I'll just say that. Well, it's because in reaction 1, the atom economy would be lower because there's a side product of CO2 that's being formed. So atom economy of reaction 1 is lower. Due to side product of CO2 being produced. You see, do some of these questions quickly. I'm talking, I'm still getting these questions completed. I say that like I haven't got my A-levels done already, but, you know, I've got now 10 minutes, 10 and a half minutes to do 6 minutes worth of questions, right? So, question 2. Aspirin tablets have important medical uses. Student carry out the experiment to make aspirin. Method is given below. Do I usually need to read this out? Weigh 2 grams of... The equation for reaction is shown below. Calculate the maximum mass of aspirin that could be made from 2 grams of salicylic acid resin. You see, this is what I mean. Like, sometimes you just need to go through this and just look at all the questions, because like I saved a lot of time just instead of by just going straight to the point here, going to A quickly. I realize I don't actually need all of this here. I don't need to read all of that. The main thing is here. All the information I need is here. Calculate the mass of aspirin. This is just a moles and amount of substance question. Calculate the maximum mass of aspirin that can be made from 2 grams of salicylic acid. Moles of C7 or salicylic acid, H6O3, equals to 2 over 138. They've given it to you there. They've even calculated it for you there. So 2 over 138, 0.0145, 0.0145 moles of... It's a 1-to-1 molar ratio, so 1-to-1 molar ratio, so therefore moles, I should say it's therefore, so I want to say so moles of C9H8. This is just to make sure you get the mark. You don't actually need to write this in, you can write it, I guess, but just to show the person's marking, you understand what's going on, and just make sure your examiner realizes, the one thing you don't want your examiner to do is, how did he get that number there? How did he get that number there? How did he get that number there? Where did he get that number from? By just saying the statement saying, because it's a 1-to-1 molar ratio, so the moles of C9H8O4 will also be equal to 0.0145. They know what you're trying to talk about, but just making sure it clears out, it makes it less stressful for them, and you're more they're less likely to drop your mark by accident. That's a voice crack, that's bad. Anyway, to calculate the maximum mass, which is a theoretical mass, really. No, it wouldn't be a theoretical mass, it's in our reaction, it's the amount that they gave us. Moles is equal to mass over the MR. I talk too much. I talk way too much. If the moles is equal to the mass of the MR, the mass is of... How much space is the mass? I think it's quite a lot of space. Mass of... Is this even in shot? Oh, it's not even in shot. All this time I thought it was in shot. Are there other questions in shot? Hopefully they were in shot. I can't even see from this angle. But hopefully all the other questions were in shot. I tailored it to my iPad specifically, so in case you need to go back. Yeah, just make sure. Alright, so mass of... How much time we got left? We've still got 7 minutes to answer, and we're already halfway through this now, or started it. Mass of salicylic acid. No, it is a theoretical mass. What am I talking about? We're making the point. It's a theoretical mass. Mass of C9H8O4 is equal to 0.0 moles. So mass is equal to the moles times by the MR. 0.0145 multiplied by 180. 180, which is equal to answer times by 180. 2.61 grams, which is 2.61 grams if you round it. 2.61 grams. Alright, the student made 1.1 grams of aspirin from 2 grams of salicylic acid. Calculate the percentage yield of this aspirin for this experiment. If you didn't get it, okay, so it's just you. If you we already know this. So if you didn't get the answer, they'll give you an answer that's there, but it's not the correct answer. But since you've already worked out the correct answer as being 2.61 grams, we can just do 1.10 grams over 2.61 times by 100, and that's our percentage yield right there. So 1.1 over 2.6, think just pretty much have to use the answer. %42.2% roughly. So 42.2% if you round it. 42.2%, which is realistic. When you actually, this is also practical. Making aspirin is a practical from salicylic acid. It's a lot more complex than this. I think it's kind of, there's a lot more steps to using a Bocklin funnel. I think this might be a GCSE question. In the real exam, it's a lot more complex than that. Alright, 4 minutes now to answer two markers. Alright. Suggest one possible reason for why this method doesn't give the maximum amount of aspirin. Is there anything more than this? No. This is just one of the reasons why percentage yield isn't high. You can just say some of the reactant was lost during the reaction, was lost during the reaction. Concentrated sulfuric acid is as catalyst in this reaction. Just how the use of catalyst might reduce the cost in industrial production of aspirin. With catalyst, it's only 1 mark really, so it will just reduce the temperature. You can use a lower temperature, which would reduce cost of catalyst, reduce the activation energy. I'm just waffling. All you need to really say is that it would reduce you can use a lower temperature, so that would reduce cost. So catalyst reduce the activation energy, but so a lower temperature is used. I can't write. Reducing costs. Alright, that's the end of the video. Hopefully it was helpful. Bye.